Okay, so today we have with us Pavel Mancera Piña from Leiden Observatory. Pavel is visiting us today and tomorrow. He's at Maria's office in the second building next to the seminar room. So you can visit him anytime you want to base there. Pavel obtained his bachelor degree in Mexico. He's originally from Mexico, and then moved to carry out the master and PhD at the, what was it?
In Groningen.
In Groningen, the University of Groningen, Captain Astronomical Institute. And now, well, he moved to as a postdoc to Leiden Observatory afterwards, and now he's a Veni Fellow from the Dutch Research Council, so at Leiden Observatory. And he has been awarded several awards for the bachelor's degree, for the master's, and he got a NOVA master and PhD fellowship, and a Van Swindernein PhD thesis prize as well. And he's an expert in dark matter halos, and today he's gonna talk about extreme dark matter halos of gas-rich ultra-diffuse galaxies. Thank you.
Thank you very much for this very nice introduction. Thank you very much to all of you for being here. I'm very excited to have this opportunity to tell you a bit more about some of the research that I'm doing regarding these ultra-diffuse galaxies. Before going into the subject, I just very briefly want to mention what are some of my interests, because I know that there is a very broad, the Institute has very broad research interest as well. So here I just have a slide with some of the highlights. In particular, I'm very interested in the connection between galaxies and dark matter halos, understanding the baryon cycle, and I look into this by means of studying the kinematics and the dynamics of galaxies, and looking, for example, at the origin and the consequences of the existence of scaling relations. And I do this both at low and at high redshift. And here, just as a highlight, so I am highlighting essentially some of the works in which I have been involved or in which I'm currently involved. For example, regarding to my PhD thesis, which has the title Dark Matter and Angular Momentum in Revised Galaxies. I looked at things like the vertical structure of the gas disks in galaxies, the relation between mass and angular momentum, and how is the angular momentum in galaxies regulating their evolution, their gas content, their star formation. I have also looked at things, well, this is essentially showing the baryon fraction in galaxies relative to the mass of the halo, so to understand, essentially how many baryons galaxies retain as a function of the mass of the halo, and also looking at the impact of those baryons into dark matter scaling relations, such as the concentration mass relation. This was mostly at low redshift. At high redshift, I'm involved in different projects. For example, I'm leading the kinematic efforts for the SUSPENSE program. SUSPENSE is a cycle 1 JWST program that is obtaining essentially the deepest ever mid-resolution optical resonance spectra for quiescent and star-forming galaxies at redshift between 1 and 3. And also, I use a lot of ALMA observations in general, or IFE observations in general, to constrain the kinematics and dynamics of galaxies. So if you have any interest in any of these things, I'm very happy also to talk about these things with you. But today, in fact, I'm focusing on these extreme galaxies with extreme halos. Now, again, I will start with a brief introduction just to make sure we are all on the same page. And this introduction begins with dark matter. So we know that dark matter dominates the mass budget of the universe, and because of this, it governs gravity, and it is essential for the formation of structures in our universe. Now, in particular, when enough dark matter gets agglomerated, dark matter halos will form. And a very early result from embodied cosmological simulations was that the density profile of these dark matter halos is typically very well described by relatively simple functional forms. And most famous of this is, of course, the Navarro-Franken-White the NFW profile. Profiles like the NFW profile are usually described by two parameters, namely the mass of the halo and the so-called concentration parameter that simply quantifies how concentrated or diluted is the halo. So we can see this example, three dark matter halos of the same mass, but the halo with the higher concentration has more mass in the inner regions and less mass in the outer parts compared to halos with lower concentrations. So in principle, one could take any combination of halo mass and concentration and form dark matter halos. But another result from these simulations is that these parameters are not random. The halos that are produced in simulations don't have random combinations of halo mass and concentration. And instead, there is a very clear anti-correlation, the so-called concentration mass relation, that tells us that halos that have galaxies with lower halo masses have higher concentration parameters. So this is a cornerstone prediction from CDM. When you look into the variance, and you can do this by adding variance into the simulations or using techniques like abundance matching, it's also very clear that the baryonic content of galaxies is connected with the amount of dark matter. For example, this plot shows, I don't know if you can see, but essentially it's the baryonic mass divided by the halo mass, normalized by the cosmological baryon fraction, so the average amount of baryons in the universe. And what we, the picture that we get from, for example, abundance matching is that galaxies are essentially very inefficient at retaining their baryons. In particular, when you go to the low mass regime, they have a very low baryon content. Now, these are expectations from the theory, but we can actually go and test this with real data, which is what we want to do to constrain our galaxy formation and evolution models. And one of the best ways to do this, at least for nearby galaxies, which is some of the things I mostly study, is looking at gas kinematics. And in particular, in the nearby universe, a great line to do this is H1, so it's the 21 centimeter emission from the neutral atomic hydrogen. And by looking at this emission line, we can build, for example, these two types of kinematic maps. On the one hand, we have the velocity dispersion field. So this tells us about how turbulent is the gas in the disk of the galaxies. So this informs us right away about the processes driving the turbulence in the ISM. And we also have the velocity field telling us how fast is the gas moving at different positions of the galaxy. Now, of course, the velocity field is a consequence of the underlying mass distribution or the underlying gravitational potential, and therefore we can use these observations to trace the dark matter in galaxies. This is not new. This has been done for about 45 years. And as you know, this also provides one of the clearest evidence for dark matter in galaxies, because the idea is that if we were to observe only the stars and gas in galaxies, compute with integrals, essentially the velocity implied by the mass distributions, we will expect galaxies to rotate very slowly in the outer parts where there is little mass. So some sort of a rotation curve like the blue one here. This will be from the variance. But instead, our observations show that the outer parts of galaxies rotate very fast, and we understand this as an additional component, which is the dark matter halo, that provides essentially the match that you need to the observations. Now, of course, you can, using the rotation curves, you can find the best fitting dark matter halo, and from the velocity of dark matter halo, you understand right away what has to be the density. Now, as I said, this has been done for about 45 years or so. So what is the new aspect in all of this, or how am I trying to study this in the context of these ultra-diffuse galaxies? Well, first of all, I want to introduce ultra-diffuse galaxies, or UDGs by short. By UDG, we simply mean these are dwarf galaxies that have effective radii larger than 1.5 kiloparsecs, and they have surface brightness fainter than 24 magnitudes per square second. This is a very observational definition that you can see here right away. So these UDGs have large effective radii, comparable to, for example, the size of big spirals like the Milky Way, but they are extremely faint. Because of this, you can barely see them in the images probably, but I promise you there are galaxies here. They are extremely diffuse. And in terms of, if you want, of more physical quantities, what we have is that at fixed mass, these UDGs, which are shown here in pink, so you see stellar masses of dwarf galaxies, 10 to the 9, 10 to the 7. They are the largest galaxies. So because of this, they are very diffuse, and also they will have very low star formation rate surface densities. Now, because they are so faint and so hard to detect, this is a fairly unexplored galaxy population, and we were very interested to understand whether being so extreme in terms of size and in terms of surface brightness, whether they are extreme also in other properties, or this is simply a normal galaxy population.
So
Yes.
the actual size, you say, so if they are so diffuse, how do you find the size? So they
Yeah. So I think the key point here is that to quantify the size of the galaxy, we use the effective radius, which is not the size of the galaxy, but is traditionally historically used. And the advantage is that so first of all, indeed, you need deep service. For example, if you use things like SDSS Sloan, they are quite faint, so you barely see them there. So you need to go a bit deeper. The advantage is that as soon as you get the brighter part, you constrain fairly well the effective radius because the outer parts contribute very little to the total emission. So that's how you can, despite the fact that they are very faint, if your photometry is deep enough, you can obtain robust constraints on the effective radii. Yes, yeah, for sure. And this will also depend, of course, on limitations from the telescopes and the distance to the galaxy and so on. So the question that we were aiming to answer was whether we can test our galaxy evolution models using these extreme galaxies. And as you can imagine, my preliminary answer is yes, because otherwise I wouldn't be here giving this talk. And in particular, among this UDG's population, I'm looking at a subset of them that have a lot of gas. So we call them gas-rich UDGs. A few years ago, Luke Lisman and collaborators, essentially they match SDSS. So they said, okay, according to SDSS, how many of these ultra-diffuse galaxies we find? That also have an H1 detection from the alfalfa survey. And they found 120 of these systems. And you can see here in this plot that shows the H1 mass as a function of the stellar mass, that these systems are heavily gas dominated. So for stellar mass, typically around 10 to the 8 or below, they have an H1 mass around 10 to the 9. So this means that even though they have a stellar mass about 1,000 times, for example, lower than the Milky Way, they have the same gas as the Milky Way. So the typical gas fractions are 10 to 90%. So they are extremely gas rich. Now, this where alfalfa is a survey done with Arecibo, so it's just a large but single dish. So you only have unresolved information. You don't have spatial information. And therefore, if you want to study the kinematics, the best thing you can do is to look at the shape of the line globally in the whole galaxy. So you don't know spatially how is the gas rotating, but you know globally what is the shape of the H1 line. And typically it looks like this, essentially because of a Doppler shift. And in particular, if you measure the width of this H1 line, that is a proxy for the rotation velocity of the galaxy, and that's a first measure of the kinematics. Now, what people found originally with these galaxies was actually quite intriguing, because they found that if you take on the one hand these ultra-diffuse galaxies, and then you select other galaxies with similar mass, but that are not optically diffuse, these UDGs shift towards lower values in this width of the line, which is a proxy for the kinematics. So as if they were rotating more slowly. So this indicates that they may have atypical kinematics, but these results are fairly uncertain because they are based on unresolved data. And the problem with unresolved data is that, for example, you have very little information on how to project the line of sight observed rotation velocity. So you want to correct for the inclination to know the intrinsic velocity. You need to decide where exactly do you measure the width of the line. You don't have information on whether the rotation curve is flattening, whether it's still going up, that you need to constrain the dynamical mass. And it's also unclear how much of this broadening is coming from the underlying rotation and which fraction is coming from just turbulent motion, from the velocity dispersion of the gas. So that's why ideally you want to go from unresolved kinematics to resolved data. And over the last few years, we have been doing that. So essentially, we went back, to this catalog that I was mentioning a couple of slides before, and we took 6 galaxies. We went for an easy choice. We went for the most extreme objects, the 6 of them that have the largest effective radii and the highest gas fractions. Here it shows, hopefully you can see them. Even in the screen, you can barely see them. The optical images, in this case, from the legacy survey that goes much deeper than SDSS. And we follow them using H1 interferometric observations, in particular using the VLA and the Westerbork synthesis radio telescope. And I will show you these results. So the first thing we found, and I show you here 3 examples, is that these galaxies have extended disks with ordered kinematics. And you can see here the velocity fields that have the clear kinematic pattern of a rotating disk with a side that is receding, a side that is approaching. Now, we want to quantify the kinematics of these galaxies. But even though we have, for the first time, resolved observations, the resolution is still quite low. You can see this circle here, this ellipse. Those are the beam, the PSF of the observations. So you cannot just go and measure the kinematics from the velocity field because the observational effect it's a problem called beam smearing, essentially is erasing the velocity gradients. So you tend to underestimate the rotation velocity and you tend to overestimate the velocity dispersion of the gas. So it needs to be done very carefully. And in particular, we use a very well-tested software called 3D Barolo that essentially takes care of these instrumental effects. I'm saying this here in 2 minutes, but it took a couple of years for my PhD to really get a handle of how to use this software that essentially does forward modeling. So you make galaxies, you mock galaxies that you convolve with the beam of the observations until you match the data. If you want to know more details, I'm very happy to give you more. But for now, I just want to show you a bit how that our models work. And I do this by showing here the so-called position velocity diagrams. So these are simple lines, maps, sorry, of the line of sight rotation velocity as a function of the distance from the center along the kinematic major axis of the galaxy. So essentially, you take a slice along the kinematic major axis, and you see the rotation. And again, you can see that has a very clear, there are very clear velocity gradients. The data are shown in black, and the projection of our best fitting model are shown in red. So overall, we can retrieve the bulk of the kinematics of these galaxies. In this case, the yellow points are the rotation velocities. So we also find rotation velocities consistent with being tracing the flat part of the rotation curve. And this makes sense because typically we're tracing the rotation curves up to 8 to 10 kiloparsecs, which for a dwarf galaxy is huge. It's 1/3, 1/4 of the virial radius. So the parameters that we find are, in terms of the velocity dispersion in turbulent motions, around 8 to 5 kilometers per second, which is typical of our galaxies. You can explain this very easily, essentially with little feedback from supernovae with very low efficiencies. And the circular speeds of the systems are around 20 to 40 kilometers per second. So now that we have solved this technical part, that we have obtained these kinematic measurements, I think we can get into the exciting part of all this, which is looking at scaling relations, in particular dynamical scaling relations. And probably the most famous of them for star-forming galaxies is the baryonic-Tully-Fisher relation that connects the baryonic mass of galaxies, meaning stellar mass plus the mass of the cold ISM, as a function of the circular speed that, of course, has a contribution from the baryons and from the dark matter. And I show you here the relation for 3 different galaxy samples. The relation seems to have a very low intrinsic scatter, and it has many different applications. You can use it to measure distances. You can use it to measure the Hubble constant. It's a strong prediction from alternative dark matter theories like modified internal dynamics. You can use it to test your galaxy evolution models. So many different applications. Now, given the baryonic masses that we measure for our galaxies, we expect them to be in that orange region there. And they should be there because galaxies follow the baryonic-Tully-Fisher relation. Except that these galaxies aren't there. What we're finding is that they are strong outliers of the relation. And specifically, they seem to have circular speeds, which are a factor 2 to 4 lower than galaxies with similar baryonic mass, or they have a baryonic mass a factor 10 to 100 larger than galaxies with similar circular speeds. So they're really strong outliers. Now we have tried to put the galaxies back in the relation by thinking of different systematics like the mass-to-light ratio, the distance to the galaxies, non-circular motions, inclinations, but essentially we don't find any way in which you can put the galaxies back in the relation. And again, if you want to discuss more about this, I'm also happy to go over each of these potential systematics. But what we conclude from this is that indeed these galaxies are of the Tully-Fisher relation. Now this by itself, I think, is quite interesting because this is the first known galaxy population to systematically deviate from this relation. But there is something else that I find quite interesting that we can see here with this couple of lines. So the black dashed line is a theoretical expectation, the theoretical relation between the circular speed at the virial radius and the virial mass of dark matter halos. So if you want, this is the Tully-Fisher for dark matter halos. Now, if you multiply that by the cosmological baryon fraction, so roughly the average amount of baryons in the universe, you end up with the gray line, which is therefore the expectation where galaxies would lie if they had a baryon fraction as high as the cosmological average. And what we find, quite surprisingly, is that within the uncertainties, all our galaxies are consistent with this line, which means they are consistent with having a baryon fraction as high as the cosmic mean. Now, this is quite surprising because, as I was showing in the introduction, as we can also see here, typically compared to the mass of the halos, where galaxies have low baryonic masses, so they have low baryon fractions. So what we think that is happening is that these galaxies, they are isolated. I don't know if I mentioned that, but they are selected to be isolated. So if you're isolated, you are less likely to have a massive neighbor to get your gas. Now, because they have very large sizes, they have very low star formation rate surface densities. So what we think might be happening here is that this is a population of galaxies where feedback failed, in the sense that feedback was not powerful enough to drive massive outflows beyond the viral radius of the galaxy, so the gas can be reaccreted. And because there are no massive neighbors around, the galaxies can keep the gas there for long time scales. So we think that's why you end up with such a high baryon fraction. Not expected, at least at first sight. Yes.
They are isolated because they are easier to find as clusters, or because you do not expect this kind of galaxies to live in groups.
Yeah, thanks for the question. I didn't explain that very well. So these ultra-diffuse galaxies, you find them in all different environments. Actually, by numbers, you find them at most in galaxy clusters. There's a very clear relation between the number of VDGs you find as a function of the mass of the cluster. So you can find hundreds of them in clusters, but we also find them in lower mass galaxy groups and in isolation. So the sample that I am working with, they are by selection isolated. That's also why they have so much H1, because of course the H1 will decrease when you get closer to massive neighbors. So in general, UDGs can be in very different environments, but this particular subset, they are isolated. Yeah, they are very gas rich. So yeah, that's quite interesting, right? Because it also tells you that whatever you find about them in principle cannot be attributed to the environment, at least not recently. Now, given this idea that I was just proposing, that the high baryon fractions are connected to the large effective radii and the isolation of the galaxies, we would expect that this gap here, that there is no gap between our galaxies and the baryon-to-Fisher relation. This whole region of this parameter space should be populated. At least that's what we thought back in 2019 when we published this result for the first time. And we were arguing that because these galaxies are very faint, they need a lot of time to observe them. Probably we just haven't discovered them. Now, very interestingly, over the last year, there have been a few studies looking at this gas-rich EDG population, and they find the following. Essentially, again, this is the baryonic-to-Fisher relation. My galaxies are like over here in blue points. And what they find is a whole set of galaxies, indeed, bridging this gap between the typical baryonic-to-Fisher relation and the most extreme of the galaxies that I studied. And it looks like this also in the baryonic-to-Fisher relation, if you compare VDGs with dwarfs, is there only for the ultra-diffuse galaxies, so those that have extended sizes. And even within ultra-diffuse galaxies, if you compare those that are not isolated with those that are isolated, you find that the offset is mostly coming from those that are isolated. So it looks like really this offset is regulated by a similar mechanism to what I was mentioning. Now, a big caveat here is that there are so many galaxies here because they use unresolved data. So this is using alpha data, essentially, again, using some correction for the inclination and using relatively faint photometry. So on a galaxy by galaxy basis, each of these things has a large uncertainty, but I think as a statistical test, it's quite interesting because it tells us that this population really systematically deviates from the relation. And we also have a couple of papers that should appear soon on the archive showing a few more galaxies with resolved observations, essentially populating this gap. Now, what happens with the dark matter halos? Because if these galaxies have so much variance, and yet they rotate very slowly, that tells you right away that there has to be something atypical on the dark matter distribution compared to other dwarf galaxies that rotate, that have the same dynamical mass essentially, but much lower baryonic mass. So the question here is, can these ultra-diffuse galaxies tell us something about the nature of dark matter itself? And the way in which I am studying this is again using rotation curve decomposition. So the idea is that if we measure accurate kinematics and we observe carefully the stellar and gas distributions, we can isolate the contribution from the dark matter. Now, to do this, you really need to have very, very good data, and we didn't have that in the degree in which we wanted. So the typical data I was working with before looked like that. So in terms of the H1, they were based in 6 hours using the VLA with a spatial resolution about 15 arcseconds. So you can resolve some substructures in the H1, but not too much. And in terms of the photometry, we were using a 3.5 meters telescope in the US, more or less using G and R with about an hour and a half on each band. So the images were deeper, they are deeper than SESS, but still you can see, you sort of see a blob here in the middle, so you don't understand if even the galaxy is associated with the H1 because the sizes are completely different. The position angle also seems different, so it wasn't very clear what was going on. So we started an observational campaign to improve this data. So now in terms of the H1, we added about 50 hours of the VLA. So this allows us to trace the resolution a factor of 3 times better. And in terms of the stars, we use the Gran Tecan telescope in La Palma. This is the largest optical telescope in the world, 7.4 meters. And we observe for 10 hours in 2 different bands this galaxy, with which, as far as I know, these are like the deepest optical observations taken from the ground. So I will show you now how the data look like. So just remember the H1, you resolve it more or less. The stars seem to be disconnected with the H1. However, the new data reveals something quite different. So now we can see that what we were looking at before was just the central redder region, but there is a whole extended blue, very blue disk that even has spiral arc-like features. And importantly, also we can trace now much better the substructure in the gas, and we can see that the morphologies of the stars and of the gas match fairly well. So with this, we can now constrain very well the contribution from the stars and gas to the potential, and thanks to our new kinematic model, we can then fit for a dark matter halo. And now let me show you what happens when you do this rotation curve decomposition. Now, for starters, you need to choose which type of halo you are going to fit. And here I am using a so-called core NFW profile. So this is an NFW, but it has an extra 2 degrees more, two more free parameters that allow the density profile to develop a core. So that accounts for the fact that many dwarf galaxies have dark matter cores. And then you have as other for the main two main free parameters are the halo mass and the concentration. So this is the mass model. So the contribution coming from the stellar disk is shown in orange, the contribution from the gas is shown in blue, and the best fitting dark matter halo is shown in black. So when you add all those things in quadrature, you have your best fitting mass model in red, and the band is the 1 sigma uncertainty. So in principle, the fit is great, right? I mean, you can explain very well the kinematics of the galaxies, but there is a price you have to pay to reach this very good agreement. And it's the fact that the mass of, so these galaxies have baryonic masses of around 10 to the 9 solar masses, and the mass of the halo that this best fit has is a few times 10 to the 9. And the concentration parameter is around 3. So if we look at the same plots that I was showing to the introduction, so the galaxy will be somewhere here, so 10 to the 5 times 10 to the 9, concentration of around 2 or 3. And the baryon fraction will be even higher than the cosmological average is here at 1, the logs here. So it will be even above the cosmological fraction. So, I mean, we think that there are so many scenarios under which these galaxies could form, and I'm happy to discuss those things. But as an additional extra check, we said, you know what, let's forget for a second about the concentration mass relation, allow it to keep it as a free parameter. But in terms of the halo mass, we can always set a minimum halo mass in our fit to ensure that you don't violate the cosmological baryon fraction, so you remain below 1. So when you repeat the fit having a lower limit on the halo mass, you can you find now by construction a more massive halo around 10 to the 10 solar masses. The concentration is extremely low, around 1, but you can still fit the kinematics relatively okay. I mean, the agreement is not as good, especially in the outermost point, but with the uncertainties, one could claim the model is acceptable.
So can I ask you something?
Yes.
So the things that you have observed here is the circular velocity, the total circular velocity, and you have figured out which part of it is due to gas, you can attribute to gas, and which part you can attribute to stars.
Yes.
So that you can fit the halo component. Right?
Exactly. Yeah, yeah.
So they modified the NFW with 4 parameters.
Yes, I mean, yeah, it has 4 or 5 free parameters, but you can always put some Gaussian priors. But the main parameters are the halo mass and the concentration. The additional parameters are there here essentially. Is the size of the core that it fits and the degree of coreness. I can show it also the equations. But essentially what this builds is a halo that has a core in this case of a half a kiloparsec, for example.
So, sorry, may I ask one more thing? So these extra parameters like the core radius will mostly affect the inner regions of this plot, not the outer ones.
Absolutely.
Whereas the concentration should affect the whole profile. So the whole profile that we see here, right?
Yes, yeah. I mean, the size of the core, yeah, you are right. I mean, it affects mostly the central regions. The concentration is also mostly given by the central regions, but it has a more global effect. I mean, it extends more. Yeah.
That's good. Just understand what.
Yeah, no, thank you very much.
The points to which you're fitting, are they this 5? Or
5, yes.
and how many?
So again, depends a bit, but essentially in this case is 3. In this case, are 3 free parameters, because for this specific case, is the mass of the halo, the concentration of the halo, and the size of the core. For simplicity, we are assuming that the core is that the profile is fully cored. So you have these 3 parameters. Yeah. And well, sorry, I didn't mention here, but we also, to make sure we have all the uncertainties taken into account, we include as a nuisance parameter the distance and the inclination. But these follow Gaussian priors based on our measurements. So we just allow them to vary a bit so that we can account for the uncertainties. So I think what this exercise tells us is that regardless of whether or not you impose this lower limit on the halo mass, you always end up with these low concentration parameters and with extremely high baryon fractions. In one case, higher than the cosmological average. In the other case, below the cosmological average, but much higher than typically observed. So just for reference, even in this case, the halo mass is 10 to the 10. Typical stellar to halo mass relation, we'll expect something like 10 to the 10.7 to the 10.5. So almost an order of magnitude higher. Now, this great data, we only have it for one galaxy, but we can use the lessons that we learned from this high resolution deep data to fit the other galaxies in our sample. And we have done this. This is work led by the Malgong and Haihui Yu in Riverside. And essentially what we find is that, again, if you look at the concentration mass relation, these galaxies shift off compared to the prediction from CDM that other normal galaxies seem to follow. If you take this at face value, this is something like, depending on the galaxy, it goes between 5 to 7 or something like that, sigma attention with respect to CDM. So the next question that we have was whether this type of halos actually do exist in cosmological simulation, because maybe these halos are actually there. And to answer this, we looked first at TNG50. Essentially, it's one of the few cosmological simulations that have fairly large volume with decent resolution. And we looked at the concentration mass relation in TNG50. And we were quite surprised because this is again concentration and mass. These are simulated halos, each of these points. And what we see here is that most of the halos follow the expected concentration mass relation. This is the same plot that I was showing you before. Then there is expected scatter. In this case, this is 3 sigma here. You can see it's symmetric. You can imagine the line of plus 3 sigma on top. But what is unexpected is this state here of very low concentration parameters. So these halos, this is not symmetric, right? There are no halos with very high concentration. This only happens in the low concentration regime. So these very extreme halos actually, in principle, seem to exist already in this type of simulations. Now, something that is quite promising is that if you take at similar halo masses, you take those halos that follow the concentration mass relation. So this shows the concentration of the halo relative to the median. So these are things that follow the median concentration mass relation. And then you contrast those with galaxies with simulated halos that have very low concentration parameters. These two groups have, on average, different spin of the dark matter halos. And the reason why this is interesting in the context of these galaxies is because, in principle, if UDGs have a higher spin parameter, one will expect the angular momentum of the halo to be inherited to the baryons, and that high angular momentum in the baryons will explain why they end up having a larger effective radius. So it's quite promising because this would provide a natural explanation for how to form UDGs, which is by itself a heavily discussed subject. Now, not everything is great, and I think this is also quite interesting because even though when you look at the concentration mass relation, you see an overlap between our measurements and simulations, this overlap is not 100% correct. And in particular, we see this from this plot that shows on the y-axis the circular speed inside 2 kiloparsecs for a dark matter halo. So this is a proxy for the inner density of the halo, right? Because if it's denser, you would have a higher circular speed inside 2 kiloparsecs. So it's a proxy for the central density of the halo as a function of the maximum circular speed of the halo, which is a proxy for the halo mass. So what we find is that even though, again, they have global concentration parameters that are similar to the observations, simulated halos are systematically too dense in these small scales of around 2 kiloparsecs. So, so the agreement is not great. Now, one could think about baryonic physics, right? Because we know that different theories predict that thanks to probably repeated supernova feedback from Borsig star formation, you can generate dark matter cores. But at least in TNG50, stellar feedback doesn't drive dark matter cores. It will be very interesting to study this with different simulations. But for the moment, we conclude that at least for DNG50, feedback doesn't do the trick. Yeah. Yes.
Forget. But you said that when you fit your curve, you already take the maximal corners.
Yes.
So then what those simulations are if they are not real?
Yeah. No, that's a very good question. Yeah, because that's a bit, it's not fully consistent, right? Because this, so the fit that it's the dark matter halo profile fitted to the galaxies assumes a full transformation of the core, while these profiles are not cored. So two things to take here into account is that not all of the fits prefer a core. Sometimes you have a fully core profile, but the radius of the core is whatever, 10 parsecs, just to say something. So sometimes effectively, the core is smaller than the softening scale of the halo. So in the simulations, you wouldn't see it as a core. So yeah, I think that's the main thing. And essentially, but it's true that some of these halos, for example, could be unrelaxed halos, and that's why even though so the outer parts are a bit tricky, and that's why even though they don't have cores, you will assume you will see a low concentration parameter. Yeah. And then I'm about to finish. We wanted to test whether if stellar feedback, if baryonic physics cannot do the job, whether dark matter can do it. And a particular type of dark matter that we were very interested in is self-interacting dark matter of SIDM. That, as you know, cold dark matter doesn't interact. Cold dark matter particles don't interact with each other, while instead self-interacting dark matter, they do interact. So they have an effective cross-section that regulates how often or how easy are the interactions taking place. There are different theories about how to couple this idea with the standard model. I think one of the ideas that people usually like is that perhaps the self-interactions occur when you exchange a dark photon, things like that. But for our purposes, what really matters is that the self-interactions are there, and what happens in self-interacting dark matter is essentially what this plot shows. So this is the evolution of dark matter halo in self-interacting dark matter. This shows the central density as a function of time. So in principle, every halo in SIDM will go through a phase like this. Namely, it's going to expand at the beginning because of the self-interactions. So in the center, you have lots of interactions. You are thermalizing the halo, so you lower the densities. So this will create a core without stellar feedback. So that's the expansion phase. And then at some point, essentially, you don't have enough self-interactions to keep driving to be stopping gravity. So then it's going to start collapsing. Now, the reason why this is quite interesting is because we know that CDM has a huge success at large scales, and SIDM can recover the same success at large scales, because at large scales there are little self-interactions, so you obtain CDM. But at low scales, when you can have this type of phenomena, you can solve, for example, the cosp core problem, because as I said, you can create cores without stellar feedback. And also the so-called diversity of rotation curve problems, and this is illustrated in this panel, because it shows that, so because this process happens for all the galaxies, this onset of the collapse actually depends on some parameters like the mass of the halo, the concentration. So for some galaxies, this may have the time for collapse might be 20 gigayears. So we will never see them. These galaxies will always be cored. For some galaxies, it might be, I don't know, 1 gigayear. So then by the time we observe them, these galaxies, so you might this curve shifts, so they will be like this. So you will end up with galaxies that are very cosby. So SIDM, the advantage is that it can produce both profiles that are cored with respect to CDM, which is shown here in black, or also even more cosby. No, someone was going to test now. Okay. Now, so essentially what we did was taking an analytic profile for a self-interacting dark matter halo, and we fitted again our galaxy, and these are the results. The plot on the left, again, is no constraint on the halo mass. It can be as low as it wants. In the other one, we have, again, the constraint of the lower limit on the halo mass. Now, what we find in general is that, especially when we allow the halo mass to be whatever it wants to be, the fit is very good. It's as good as in the case of CDM. When we impose the lower limit, again, the last point is underestimated. The rest of the points seems fairly fine. But what is important is that the cross section that you need to do this match, around 130 square centimeters per gram, is actually what you would expect from theory in the context of SIDM. So in that case, they are consistent with each other. The other thing to highlight is that the concentration parameters that you need are still low. You can see here 4 in one case, 2 in one case. So this low concentration parameter problem seems to be there. But what is quite interesting is that it looks like this is not a problem for SIDM. Now, this plot shown here, this is work by Ita and Adler, and essentially what they did was running a cosmological simulation. This is not a DNG50, this is a universe machine, perhaps. I need to check it out. But what matters is that they run a simulation with CDM, and they find the same results we found before. Halos in CDM are too dense inside 2 kiloparsecs compared to the observations. But if you instead run simulation allowing for the self-interactions, now these halos naturally have lower densities, and many of them are consistent with those galaxies that we observe. So the conclusion from this is that opposite to the CDM simulations, in SIDM, you can match the kinematics of the galaxy, and the parameters of the dark matter halos that you need seem to be produced in this type of simulations. And I think, yeah, on this I know I want to present here my conclusions. I would love to discuss with you these things. And I think the 3 main points of this talk are, first of all, that at least some gas-rich ultra-diffuse galaxies are strong outliers of the baryonic-Tully-Fisher relation. As you saw, they have very low circular speeds, they have very high baryonic masses, and this makes them have extremely high baryon fraction. So depending on how you perform the fit exactly, the typical variable fraction relative to the cosmological average are about 50 to 300%. For reference, a typical dwarf galaxy might have 5%, 10% at most. And finally, the dark matter halos have extremely low concentration parameters that seem to be rarely produced in CDM cosmological simulations, but they seem to be more easily achieved in dark matter halo, in dark matter type like self-interacting dark matter. I didn't show you now, but if you want, I can show you a bit later. We have also tested, for example, with fuzzy dark matter, and you find something similar that you can reproduce the kinematics. So yeah, that's it. Thank you very much for your attention, and I'm happy to take questions.
Excellent work. You did excellent work.
Thank you.
Congratulations. So the way I understand it is that you can basically kill more. The second thing is, do you have mass metallicity relations for this work?
No. So the first question, yes, absolutely. I mean, one of the strongest or cornerstone predictions of MOND is that the baryon-Fisher relation will have a slope of 4 with zero intrinsic scatter. So the fact that these are isolated galaxies that don't obey the baryon-Fisher relation already, is in strong tension with MOND. Something else that is quite interesting, speaking about MOND, is that you can also, so the prediction from MOND is to Fisher, so that's already in tension. But you can also compare the observed rotation curve with the MOND expectation. This is the galaxy for which I was talking today. This is another galaxy that shows similar properties. The observations are in gray, and in red are the MOND predictions. So you can see they strongly overestimate the circular speeds of the galaxy. And you can do things like, you can do the exercise. Which inclination do we need to match MOND? But the inclinations are essentially the galaxy will need to be face on, while we see the galaxies, especially that one, is not face on. Or you can do the trick of saying which type of acceleration parameter I need to match the data, and you need something like 100 times less than this proposed universal constant by MOND. So yeah, in this sense, these galaxies cannot be explained with that phenomenology. About the second question, unfortunately, we don't have measurements of the metallicity, mostly because they are very faint. So at some point, I run some exposure time calculator for some telescopes, and I said, okay, maybe at some point, but it will be something indeed very interesting. I think both to get the metallicities and potentially, but of course, you will need even higher signal to noise ratio to try to get star formation histories. Also, because if these things really have low concentration parameters, you might expect to see an imprint on that on the star formation history, because they should form later than average in the universe. We have stellar masses based on essentially on the colors. So we have the photometric observation, so that allows us to trace the luminosity profile, typically in optical bands like G and R. And then, because we typically have 1 or 2 colors, we can use these calibrations between the mass to light ratio and the color that exists in the literature. Yeah, no, I mean, if you know the stellar, yeah, but then you have to assume that they follow the mass-metallicity relation, which we don't know. But yeah.
So there's no way of, I don't know how many photometric points you have to in order to assess the stellar population, not the star formation rate history, because that's kind of stellar distribution.
Yeah, no, so essentially, so this shows essentially these are surface brightness profiles. These are color profiles. This is G minus R, G minus I, R minus I, and that this is the stellar mass surface density profile. That essentially is built by taking the surface brightness profile in the R band combined with these colors. So I think that the best thing we could do is see, okay, in the center the galaxy has relatively red at 0.4 or so in G minus R colors, and in the outer parts around 0.2. So if you take, for example, the Vazdeki's stellar population synthesis models, for typical, depending we don't know the metallicity. So if you assume that they more or less have similar metallicities as dwarfs, you will expect the central regions to be something like 2-3 gigayears old, and the other parts to be something around 1 gigayear old. But that's more or less what we can say in terms of ages.
So they are not really, yeah, well, we will see them if they were actively forming better.
No, they are not there. They do form some stars because you can see in the optical image that there are some blue that's there with the star formation. So for sure they have some star formation each now and then. But if you compute the star, first of all, there are few observations. All these things are covered by galaxies, but it's like 5 minutes. So you get some sort of star formation from the UV. But the things that are very low are the star formation rate surface densities, because again, you have little star formation in a huge stellar disk.
So sorry, what do you think these galaxies are? So they have very few, still they have a lot of gas. So they were able to retain a lot of gas. So those are, as you said before, just galaxies in which the AGM feedback didn't start, didn't ignite. They have a sign of nuclear activity.
They don't have signs of nuclear activity. Probably the stellar masses are a bit too low. So what I think right now is so it's two things. On the one hand, what I was saying a bit during the talk, I think our best guess right now is that these were galaxies that probably they tend to form later on time, which means from the tidal torque theory, we expect them to have a higher spin parameter, which we find indications of this in the simulations. If they have a high spin parameter and that is inherited to the baryons, that will explain the large sizes. So that explains the large sizes. Now, if since the moment they formed, they had very low star formation rate surface densities because of the large sizes, we think this feedback failure scenario does the trick in the sense that you never drive powerful outflows to get rid of your gas, so the gas can be reaccreted. And if they have also been isolated for all of their life, no massive neighbor has removed the gas. So potentially that will explain things that scatter around the cosmological baryon fraction. To explain things that have more baryons than the average, it's a bit more tricky. A potential explanation is that perhaps, I mean, we know that at a slightly higher redshifts, there was a lot of gas in the IgM from galaxies that actually managed to expel their baryons. So perhaps some of these baryons from other galaxies reaccreted into this type of galaxies, and they end up with more baryons than usual. But then we will expect to see the neighbors that we don't see.
Could it be just that they didn't lose the gas and the baryons because there is
that is our but I mean, I think no nuclear activity and also not even a strong stellar feedback. So
and just wait. Do you think that there can be some observation systematics that can move these galaxies from the generation away? I mean, within 10 years you have observational facilities and you re-observe this, there is a chance that they move back of the escape relation?
Yes, we have thought a lot about this, and I think so. There are 4 or 5 main sources. Absolutely, yeah. So I think it's quite robust because I will mention some of this potential systematics. So, for example, the stellar mass to light ratio. You don't care that much about the stars because the 95% of the mass of these things is in the gas. So if I say stellar mass equals 0, it doesn't affect the mass models, it doesn't move them from the Tully-Fisher relation. So you can think of distances, but the typical distance, didn't say this, the typical distance of the galaxies are around 80 megaparsecs, 100 megaparsecs. The distances come from the H1 redshift, essentially from the Hubble flow. But these are actually quite safe measurements because at the distances of 80, 100 megaparsecs, you have velocities of the Hubble flow of 6,000 kilometers per second. So the impact of potential peculiar velocities is way smaller than the type of uncertainty that you need to put the galaxies back into the Tully-Fisher or to explain the mass models because of the distance. You can think of non-circular motions that perhaps the galaxies, people have shown in simulation that if you have a strong circular motions, your recovery of the rotation curve doesn't change the gravitational potential. But at least what simulations show is that when you have non-circular motions, the effect is not systematic. You are equally likely to be overestimating or underestimating the rotation curve. So I think the fact that we have at least 6 galaxies, potentially more, all of them show this offset, also tells you that it's not about non-circular motions. And finally, I think there is the issue with the inclination. That, of course, if they are more face-on, you need to move the rotation. So they go to higher velocities in the Tully-Fisher and to higher velocities in the mass model. However, the inclination that you need are essentially that you need them to be face-on, and that is just inconsistent with the data. So we have measured this is an example. So this shows essentially in black, the black contours, black contour, white contour here, and no contour there, I think. That shows the morphology of the gas. So essentially, it's a model that encloses the emission of the gas. And then in blue, you have how the galaxies should look for the inclination correction to be large enough so that you can put them back on the Tully-Fisher relation on a normal mass models. So you can see there are some cases that you say, you know what, could be, but I think there are some cases where you just in the data, the inclination cannot do the trick. So that's why we think the galaxies are actually quite robust. Yeah.
Well, last question. Show how these galaxies deviate from the circular velocities, and then you said that we should expect some galaxies in between, and then you mentioned this population.
Yes.
The dots there. How they were selected? I mean, how did they were they found? I mean.
Yeah, so essentially this was a similar exercise as this other paper that I was mentioning before, what they did. So essentially, these people they took SDSS, in this case, I think also the legacy survey, and they did the photometry. So then with photometry, you identify those that are UDGs. And then using alfalfa, you get the distance from the H1 redshift and you get the H1 mass. And from the shape of the profile, you get the proxy for the kinematics. So then, because that's a very cheap method to get lots of data because you need very simple quantities. So these galaxies, essentially, the only selection that was done was they are typically in H1. Yes, okay. Are they ultra-diffuse according to the photometry? Yes. And so that's what you find.
With a restrictive condition on the effect the mass?
No, with the same condition in terms of sizes. So yeah, so essentially, well, for example, this work here, they took both UDGs and non-UDGs, and what they show is that are those with the large sizes, so those are classified as UDGs, the ones that likely drive the scatter.
Understand correctly here, the difference is the quality of the
Absolutely.
as a matter of fact, they don't show
Yeah, I think indeed when they show it in the others, yeah, they're yeah, well, actually, I think they show in one direction, but they are unrealistic. So that's why I think point by point, you need to take them with a grain of salt. Statistically speaking, I think that the result is there.
And those are also sources in groups.
Yes, here you have everything, and in isolation and in the field.
And
That's
this connected with the question that I asked before. Maybe in this one, the feedback did ignite, and matter of fact, they tend to a little bit
exactly. So there was feedback, and or the fact they are isolated makes a neighbor to strip away that gas. And absolutely. But yeah, here the question is about data quality. So I have now, I'm using BLA and Meerkat now to obtain a few more of these galaxies. And the plan is to submit a large program with Meerkat. Meerkat is, probably, the telescope in South Africa is extremely efficient. To give you an idea, with VLA to get like a very good quality data for this galaxy, you need like 80 hours, which we did. For Meerkat, now we're doing it with below 20 hours. So it's really powerful for this kind of service. And we plan to put a proposal to get like a large program to observe systematically more of these galaxies. Because then the idea will be, of course, to do the type of exercise we did with this last galaxy, like fitting CDM, SIDM, positive dark matter, whatever you want, but with a representative sample more than with one system. So if you are, any of you hears about this on the Meerkat panel, or you have a friend in the Meerkat panel, tell them this is very cool. Yeah.
Excellent. I think touches a lot of the